Okay, this is our last section in Chapter 5 that we're going to um, study, and it is 5.4, Sampling Distributions and the Central Limit Theorem. So we've got sampling distributions and the Central Limit Theorem. This section is really important because it lays the foundation for inference, which we'll be studying for the rest of the semester, essentially. So Chapter 6, Chapter 7, Chapter 8, Chapter 9, and Chapter 10. Now, I've already posted a video which explains or gives I think, a really good introduction to sampling distributions. So what we're going to do here is we're going to jump straight to um, finding sampling distributions and verifying their properties. And then we'll talk a little bit about the central limit theorem and apply the central limit theorem to find the probability of a sample mean. So, sampling distributions um, are the probability distributions of a sample statistic, and they're formed when samples of size n are repeatedly taken from a population. So what I wanted to do was highlight that in this course so far, we've been talking about all types of distributions, and we've been talking about um, how distributions basically are a way to describe either visually in terms of a graph or in terms of a table. It's a way of describing how your data is distributed. Okay, and so far we've talked about frequency distributions. That was the very first type of distribution we were introduced to. Probability distributions. And then we had two specific types of distributions: normal distribution, binomial distribution. And then we had a very special type, which was the standard normal distribution. Okay, so we're adding to our study, to our tool bag, a brand new type of distribution, and this distribution is called a sampling distribution. So you can have a sampling distribution of any sample statistic. You have a sampling distribution um, of sample means, of right, because sample mean is a statistic. So you can have a sampling distribution of sample means. You can have a sampling distribution of sample variations, sample um, standard deviations. Um, for us, in this course, we're going to focus on and investigate sampling distributions of sampling means. So most of what we're working with is the sampling mean, the sampling distribution of sample mean. So notice that we don't just say the distribution of sample means, we say the sampling distribution because we really want to highlight that the distribution, it comes from sampling your population. So you start off with the population and then you sample the population repeatedly, and this results in a sampling distribution. Now we have these properties of sampling distributions of sample means. The first is that the mean of the sample means is going to be the same as the mean of the original population. And the second is that the standard deviation of the sample means is going to be similar to this population standard deviation. So the formula we'll have here is that our the standard deviation of our sampling distribution is the standard deviation of our population, right, which is this is the population standard deviation, divided by the square root of n. And this n refers to the size of your samples. Okay, so it doesn't refer to the size of the original population, it refers to the size of your samples. Now we have a special word or special vocabulary terminology, standard error of the mean, or the standard deviation of the sample means. So this, you can either say the standard deviation of the sample means, or what is more common, the convention is to call this the standard error. Okay, so if you're reading articles or any research, they're going to refer to this as the standard error. You want to know what the standard error is. The standard error of the mean is just the standard deviation of the sample means. Okay, let's do this example here. In this example, what we're going to do is we're going to verify these two properties. Okay, so we're going to verify these two properties. Property 1 is this equation here, which is saying that the sample mean, the mean of the sample means is the same as the population mean. And number 2, which gives us a relationship between the standard error and the population standard deviation. So we're starting with a relatively simple scenario here. Our population is going to be these four numbers, 1, 3, 5, and 7. They're written on slips of paper and put in a box. Now, 2 slips of paper are randomly selected with replacement. So we'll reach in, pick one slip of paper, read it out, see what the number is, and then put that slip of paper back in the bag or back in the box and pick another slip of paper. Okay, so that's how the 2 slips of paper are selected. Now, the first thing we want to do is we want to compare the mean. We want to find out or compute the mean of our population. So how do we compute the mean of the population? Well, we can go into L1 and enter in the data, right? So 1, 3, 5, 7. Right, so in your calculator, L1, enter in the data into L1, and then you're going to go stat, click on stack, and then calc, and then the first option, which should be one variable statistics, one var stats. And from here you can read out that your mean is going to be 4. Now for us, we actually have, because this is a population, right, because we have the population values, we can write mu equals 4. Now what should we use for our standard deviation? We're going to use sigma. Sigma is going to be 2.236, and then the variance is just sigma squared, which is going to be approximately 5. Okay? So we're going to keep these in track because, keep these in mind, because for our 2 properties, we're expecting to use our population mean and our population standard deviation when we're finding the mean and the standard error of our sampling distribution. Okay, so let's do part B, which is to graph the probability histogram for the population values. Now this should be fairly straightforward because in order to graph our probability histogram, we need to know what are our possible values, right, of our population. 1, 3, 5, and 7. 1, 3, 5, and 7. And so these numbers are in the box or on slips of paper. What's the probability if you reach in and pick out one slip of paper that you'll get a number 1? It's going to be 1 out of 4. What's the probability that you get a 3? 1 out of 4. So the probability for each of these numbers, each of these outcomes is exactly the same. So here we'll have X is the label for our horizontal axis, and then probability P of X is our label for the vertical axis. And let's see here, so we'll have 1 is an option, 3 is an option, 5 is an option, and 7 is an option. Okay, and now if this is probability of 1, 0.5, 0.25, so then we will have a uniform distribution. So this is considered a uniform distribution. This is an example, right? It's symmetric and the probabilities are all the same, which means the frequencies are all the same. They're all 0.25. Okay, and so this is it blown up. Okay. All right. So it's important for us to gather this initial data about the population. So so far we've got the population mean, we've got the population standard deviation, and now we have the probability histogram for our population. Now let's move on to creating our sampling distribution of sample means. And I kind of wrote down here what's going to happen. Our goal is to create a sampling distribution of the sample means. Then we'll analyze this sampling distribution. And remember, we're picking two slips of paper out of the box. So that means that our sample size is going to be n equals 2. Okay, so step 1 is to list all possible samples of size n equals 2 and compute the mean of each sample. So let's do that. So in step 1,
it's 16 hours.
We need to make a list of all of the possible samples that you could get if you were to pick a slip of paper, look at what number you get, put the slip of paper back, and then pick another slip of paper, look at what number you get, and put the slip back. Okay, so we could get, first time we pick a number, we could get a 1, and then we put the 1 back in, we shake up the box, we pick again, and we could get another 1. We could get a 1 and then get a 3. We could get a 1 and then a 5. We could get a 1 and then a 7. We also could get a 3 and a 1, and a 3 and a 3, a 3 and a 5, and a 3 and a 7. We could get a 5 and a 1, a 5 and a 3, a 5 and a 5, and a 5 and a 7. And the last thing we could do, I think I need to move things over a little bit. We could get a 7 and a 1, and a 7 and a 3, and a 7 and a 5, and a 7 and a 7. We get a 7 and a 1, a 7 and a 3, 7 and a 5, and a 7 and a 7. Okay, so these are all the possible samples of size 2. Now let's compute the mean of each sample. Let me switch colors here. Okay, so in this column here we have the sample, and now we're going to put the sample mean. So for this first example here with 1, 1, what is the sample mean? The sample mean is going to be 1 plus 1 over 2, which is just going to be 1. And then we'll do the same thing with 1, 3. What's the sample mean? 1 plus 3 over 2. So that'll be 4 over 2, which will be 2. And what about this one with 1, 5? We'll get that the sample mean is 3. And then for this one, the sample mean is 4. And then here, x bar is, this is our sample. Let's see here. X bar is going to be 2, 3, 4, and 5. And now for these samples, x bar is going to be 3, 4, 5, and 6. And then last but not least, for these samples, x bar is going to be 4, 5, 6, 7. Okay, so we now have our sample means. Our sample means what is the set of our sample means? So we've got a 1, a 2, a 3, a 4, a 2, a 3, a 4, a 5, 3, 4, 5, 6, and then 4, 5, 6, 7. Okay, so do you see how we get 1, 2, 3, 4, 2, 3, 4, 5, 3, 4, 5, 6, 4, 5, 6, 7. This is like our new data set, right? We want a distribution of these sample means. So let's go ahead and move on to step 3. Find the mean, variance, and standard deviation of the sampling distribution. So how do we find the mean, the variance, and the standard deviation? Well, we can enter these numbers into our calculator. So enter them into L1. Okay, so let's see here. So let me go to Stat, Edit, and I need to clear my L1 list. Okay, so I'm going to enter in 1, 2, 3, 4, 2, 3, 4, 5, 3, 4, 5, 6, 4, 5, 6, and 7. Okay, now go to Stat, go to Calculate, one of our stats, go to calculate what we have. We'll have X bar equals 4. Aha. But now, how do I indicate that this is the mean of my sample means? Well, let me tell you. This is the mean of my sample means. It's going to equal 4. What is the standard deviation of my sample means? 1.58113883. And now to get the variance of my sample means, I'm going to take my standard deviation and square it. So 1.58113883 squared, I get 2.5. Okay. So first, while we're here, let's compare the mean and the standard deviation of my sample means to the mean and the standard deviation of my original population. So let's see here. Let's copy. Paste. We're going to resize. Okay. Okay. So notice, well, first we can eliminate that because we're not going to be concerned with that. Notice that my population mean is the same as the mean of my sampling distribution of sample means. Do you see that? They're both equal to 4. So that's the first thing. And now the second thing in terms of the properties we're supposed to see is that, remember we've got our two basic properties, is that my standard error is supposed to be the population standard deviation divided by the square root of n. Okay, so the population standard divided by n. My standard error is supposed to equal my population standard deviation divided by the square root of n. Now what is my population standard deviation? 2.236 divided by the square root of 2. Let's see what I get. 2.236 divided by square root of 2. I got 1.58. 1090763. So that's close enough, right? So they're close enough, 1.581. Okay. And so probably some rounding is the reason why we're off there. But we are already verifying, we're verifying in this case that both number 1 and number 2 are true, right? The standard error is related to the population standard deviation like so, and the population mean is the same as the mean of the sampling mean of the sampling distribution. Okay, now so we did step 1, step 2, and step 3. The last thing that we want to do is to graph the probability distribution. Okay, so now in order to graph the probability distribution for the sampling distribution of sampling means, I need to copy my new data set. Let me copy it over and paste Okay. And so now I just need to be able to, what do I need to be able to do? I need to be able to create a probability distribution for this new data set. So these, remember, are my sample means. Okay, so I'm going to write what are my sample means, and then what are the frequencies for my sample means. Remember, we're creating our probability distribution. Now, the only options for sample means, it looks like that I have 1, 2, 3, 4, 5, 6, and 7. Now, how many ones do I have? See, oh, just one. Okay, so that's going to be 1. What about twos? 1, 2. Okay, just 2. What about threes? 1, 2, 3. What about fours? 1, 2, 3, 4. What about fives? 1, 2, 3. What about 6? 1, 2, and 1, 7. Okay. So now, let me create my probability of x bar. And remember, the formula for this is you're supposed to take your frequency and divide it by n, divided by the sum of f. So what is the sum of our frequencies? So I have 1 plus 2, that's 3, plus 3, that's 6, plus 4, that's 10, 13, 14, 15, 16, 16. Okay, so this first probability is going to be 1 out of 16, and then 2 out of 16, and then 3 out of 16, 4 out of 16, 3 out of 16, 2 out of 16, 1 out of 16. So can you tell that our probability, the graph of our probability distribution is going to be symmetric? Because the numbers are going up, 1, 2, 3, 4, 3, 2, 1. So it'll be kind of like a little pyramid. So let's sketch. So in the middle, I'm going to draw the highest, which is going to be 4 out of 16, and that's going to be actually equal to 0.25. Okay? So maybe this is 0.50. So I have 0.25. And then we'll go down from there. And then we've got 2, 2, and then 1, 1. So this is 1, 2, 3, 4, 5, 6, 7. And now, watch what I label. I'm going to label this x bar because these are my sample means. And my vertical axis is going to be labeled probabilities still. So here's what we want to point out. We want to point out that we started off with a uniform distribution. This was of our population. So even though the population had a uniform distribution, when we looked at the options for the samples of size 2, now all of a sudden we've got something that is symmetric and bell-shaped. So this should remind you a little bit of kind of like bell-shaped. Do you see it's kind of bell-shaped? Of about 1.58. Okay. Ooh, forget this. Sorry. This is actually my second time doing this video because I decided I wanted to do it differently and I forgot to erase this slide. So you never saw it. Or this one. Sorry. Okay. Let's see. Okay. All right. So what we did in this long example here, I know this was a really long example, but essentially what we did was verify the properties of sampling distributions. What are those two properties? Here they are. This is what you want to remember. You want to remember that you've got a formula for the mean of your sampling distribution, and you've got a formula for your standard error. So the mean and the formula for the standard error. So we're just verifying. We verified those, and we took a look at what happens to the distribution, right? The distribution of the population was uniform, and the distribution of the sampling distribution of sample means now starts to look symmetric and bell-shaped, starts to look like a normal distribution. Okay. This is perfect. This is a perfect introduction to the central limit theorem. So here's what the central limit theorem says. It gives us conditions. Have a sample that's size 100, n equals 100, and it's going to be a lot smoother than what we have here. Do you see how this is still kind of choppy, right? What was our n? Our n was equal to 2. So here, for the first portion of the central limit theorem, it's saying if n is greater than or equal to 30, then the sampling distribution of the sampling means approximates a normal distribution. The second statement in the central limit theorem is that if the population itself is normally distributed, then it doesn't matter what size samples you're looking at, the sampling distribution is going to be normally distributed. So the sampling distribution of sample means is normally distributed. Okay. In either case, we know the center. The center is going to be the same as the center of your original distribution, right? Even if your distribution is bimodal, do you see how this is bimodal? It is not symmetric, right? Doesn't matter. You know what the mean of your sampling distribution is going to be. The mean is going to be the same as the mean of your population distribution. So we'll have the mean, that's number one. And number two, the standard error, right? So the standard error of the mean, we're going to have a formula for that. So we know exactly where the inflection points are going to be. This right here is a synopsis. The idea is that your population can be kind of like as crazy as it wants, right? And if you take large enough samples, then the samples are distributed, the means of the samples are distributed normally, right? So some of your sample means then sketch a graph of the sampling distribution of sample means. So what scenario are we in? It looks like we're in this first scenario here. We are not told that our random variable is normally distributed, or our population is normally distributed. Exactly what is our population? What's our random variable? From reading the question, we can see that our random variable x is keeping track of, what is x keeping track of? X is individual cell phone bills in dollars. So the amount of each cell phone bill. Okay, so some people have really expensive cell phone bills. Some people have, cheaper cell phone bills. But in this city, on average, mean of $63. So that means that mu is equal to $63 and the standard deviation of 11. So sigma is $11. The last piece of information we're given is that n is equal to 100. So we're taking samples of size 100. So let's see here. So we've got n equals 100. Well, actually, mu equals 63. Sigma is 11, and n equals 100. So, according to the central limit theorem, the sampling distribution of sample means, so we're going to label this now x bar, is normally distributed. Why? Because n is greater than or equal to 30. So since n is greater than or equal to 30, our sampling distribution is normally distributed. And what is the mean? The mean of our sampling distribution is the same as our population mean, which is going to be 63, so we can put our center. And the standard error, which is the same thing as the standard deviation, is the population standard deviation over the square root of n. So we'll have 11 over the square root of 100. So we'll have 11 over 10, which is 1.1. What are my inflection points? For the inflection points, remember you take your mean and you go up a standard deviation. So this is going to be 63 plus 1.1, right? Because this is our standard deviation. And you go 63 minus 1.1. Okay, for our second inflection point. 63 plus 1.1, that's going to give us 64.1. 63 minus 1.1, it's going to be 61.9. Oh, 61.9. So, tell me, what is this distribution of, right? Here, this is a distribution of sample means. What is the mean? The mean of the sample means is 63. And then what are the inflection points? And you get the inflection points by mu plus sigma, mu minus sigma. These are your inflection points. Okay, that was example 1. Let's look at another example. So the training heart rates of all 20-year-old athletes are normally distributed with a mean of 135 beats per minute and standard deviation of 18 beats per minute. Random samples of size 4 are drawn from this population, and the mean of each sample is determined. Find the mean and standard error of the mean of the sampling distribution. Okay, then sketch a graph of the sampling distribution of sample means. So I think I see before. The wording is really horrible. But the only reason why I don't want to keep changing the wording is because I would like for there to be consistent wording between your homework problems, between the exams, and between the notes here. So let me just help here. So this is the standard error of the mean. Okay, the standard error of the mean, this is denoted sigma sub x bar. So we want the standard error of the mean of the sampling distribution. Okay, so now, what is the pertinent information? We're going to read, looking for information here. Okay, the training hearts of all 20-year-old athletes are normally distributed. Training heart rates, so training heart rates are normally distributed. So this tells me that I want to keep track of X, which is training heart rate, which is, I guess, the heart rate while you're training. Training heart rate. So it could be that your heart rate while you're training is very high. Could be that your heart rate is very low. So training heart rates are normally, of all 20-year-old athletes, are normally distributed. So we can say of 20-year-old athletes are normally distributed with a mean, here's more information, with a mean of 135 beats per minute. So let's put that in. Mu is 135 beats per minute, and standard deviation of 18 beats per minute. So standard deviation of 18 beats per minute. So sigma is 18 beats per minute. Okay? Now, already our sampling distribution is also normally distributed. And now remember, if you say it's normally distributed, then I'm going to ask, what is your mean? What are your inflection points? Okay, so with what is our sampling mean? Sampling distribution mean is going to be the same as our population mean. What is our standard error? It is going to be the population standard deviation divided by the square root of n. Okay, so what is our sampling mean? It's going to be 135 beats per minute. And what is our standard error? It's going to be 18 divided by the square root of 4, right? Because random samples of size 4. So we'll have here 18 divided by the square root of 4, which will be 8/2. It means, first thing I need to do is figure out what label do I put here. Oh, this is a crappy one. Okay, that's the best I can do. The label I'm going to put on my horizontal axis is X bar because this is my sampling distribution of sample means. What is my median? 135. What are my inflection points? Well, let's see here. We need 135 plus 9, right? Because my standard deviation is going to be 9. Does everybody see that? So I need 135 plus 9 will give me 144. And then 135 minus 9 is going to give me 126. Voila. This is, thank you. And we can already get an idea of, imagine if you have a sample of, 4 20-year-olds, right? And they're training, and you take their heartbeat, and then you take the mean of their heartbeats.
Is it okay to get the garbage?
Yeah, sure,
Sorry,
sure.
I didn't want to disturb you.
No problem, no problem. Imagine if you take the mean of those 4 20-year-old athletes and say that the mean of their heart rate is 175, right? So you could look up here and you could say, whoa, 175, that's going to be literally off the chart. You know how they say it's off the chart? That's what they mean. They mean that's very far from many standard deviations away from the mean. So you could say, ooh, that's unusual for those 4 athletes to have such a high training heart rate, right? So you can kind of see the importance of being able to look at the sample distributions, because in real life we'll get samples and we'll need to know, is the sample unreasonable? Is it normal? Is it rare? Is it unusual? Is it typical? And the way we'll do that is by using the central limit theorem. Okay, let's move on to another example. So hopefully by now you're getting the hang of this a little bit. Okay, so the graph shows the length of time people spend driving each day. You randomly select 50 drivers aged 15 to 19. Well, actually, let's go back and look at this. What does this mean? The graph shows the length of time people spend driving each day. Okay, time behind the wheel. Average time spent driving each day by age group. Okay, I get it. So this is just like I guess like a cute way of presenting the information. This is basically a frequency distribution, right? So people who are 15 to 19, this is a class. Do you see how this is a class? It's going to spend 25 minutes. 20 to 24 is going to go 52 minutes. So it looks like who spends the longest time behind the wheel? 64. Oh, you know what? This cannot be a frequency distribution because the class widths aren't equal. Do you see how this class width is going to be 30? And this class width is going to be 5. And this class width is going to be 5. And this class width was 65 plus. I don't know how some people are 130 years old, right? So this is really big, the class width. So this can't be a frequency distribution because the widths aren't equal. So it's just a cute way to present the information. Graphical display of information. So we've got our different age ranges, and for each age range, we are given the time spent behind the wheel. Okay, the graph shows the length of time people spend driving each day. You randomly select 50 drivers from age 15 to 19. Okay, so then that means we select 50 drivers in this category. What is the probability that the mean time they spend driving each day is between 24.7 and 25.5 minutes? Assume that sigma is equal to 1.5 minutes. Okay, so let's see here. The first thing we need to do is figure out what is our x. In this case, x is going to equal the how many minutes someone age 15 to 19 spends driving each day. So this is a random variable, right? It depends. Some people that are age 15 to 19, they spend 0 minutes a day. Some people spend 200 minutes a day, right? So it's a random variable. And we are dealing with the sample, right? So we randomly select 50 drivers. So this tells me that my n is going to be equal to 50. Now, I know that with a sample this large, I can use let me use the central limit theorem to tell me that my distribution of sample means is going to be normally distributed. So my sample means is going to be normally distributed, and the mean of my sample means is the same as the mean of my original population. So what is the mean of my original population? I go back to this little infographic, the average time spent driving each day. So for someone in this age group, the mean is 25. So my mu is equal to 25. So if my population mu is 25, that means that my mean of my sample means is 25. And now what about my standard error? So I know that my mu x bar is going to be 25, right? Let me actually write this down. Mu x bar is equal to mu, which is going to be 25 minutes. And then what about my standard error? It's going to be my population deviation divided by the square root of n. Remember, n is 50, and my population standard deviation, 1.5. So I'll have 1.5 divided by the square root of 50, and I'm going to approximate that as 1.5 divided by square root of 50. That is approximately 0.212. Okay, now I'm ready to put in my inflection points. So, what are my inflection points? I need to go up one standard deviation. So this is going to be 25.212. And then I need to go back one standard deviation. So I need 25 minus 0.212. And I'm going to get 24.788. Right? So my inflection points, remember, are going to be one standard error or one standard deviation above and one standard deviation below. This right here, what I have so far, and this little circle here, this is telling me the distribution of any sample of people that are aged 15 to 19, that's size 50, right? So if I take 50 people that are aged 15 to 19, how far on average do they spend driving each day? This is the distribution of that data. The question I need to answer is, what is the probability, so let's erase here so we can focus. What is the probability that the mean time they spend driving each day is between 24.7 and 25.5 minutes? Now here's the deal. We want, so let me write down over here what we want. we want to compute the probability that X bar is between what and what? 24.7 and 25.5. So it's 24.7, 25.5. 24.7 and 25.5. So this is what we want to find out. What's the probability that the average time that they spend is between 24.7 minutes and 25.5 minutes? Now, guess what I'm going to do? I'm going to shade. I'm going to shade, shade, shade. Look over here. I need 24.7. So that's going to be a little bit back here. So let's say this is 24.7. Right, because 24.70 and this is 24.78 is right here. And I need 25.5, so I'm just going to go out here and say it's 25.5 is over here. I want to know, what is this area? Because this area is equal to this probability, right? So this probability, 24.7 less than or equal to X bar less than or equal to 25.5 is equal to the area between 24.7 and 25.5. So the area under the curve under the normal curve between 24.7 and 25.5. How do I find that area? That area is going to be equal to, you got it, normal CDF. What do I use as my lower? 24.7. What do I use as my upper? 25.5. What do I use as my mean? 25. What do I use as my standard deviation? 0.212. If you use sigma 1.5 as your standard deviation, you're going to get it wrong, because this is the population standard deviation. It is not the standard deviation of the samples, right? We want to know how spread out are the samples from each other. Okay? And so now what do we get when we do this? We've got space over here. Let me actually just try to copy. Paste. So this is going to be equal to, so for normal CDF, I'm going to go second bar so I can get to my distribution. And then number 2 is going to be normal CDF. My lower, 24.7. My upper, 25.5. My mean, 25. My standard deviation, 0.212. Paste. Hit enter. And I got 0.912304835. So if we randomly select 50 drivers, the probability that the mean time that they spend driving each day is between 24.7 and 25.5 is about 91.2%. So we put 0.912 or 91.2%. In other words, if we take a sample, most likely they are going to be somewhere in that range. The mean is going to be in that range. Let's do another example. Probabilities for X and X bar. An education finance corporation claims that the average credit card debts carried by undergraduates are normally distributed. Do you see how already we can figure out what X is supposed to be? Because they're telling us that the average credit card debts carried by undergraduates are normally distributed This is X, average credit card debts carried by undergraduates. Some undergraduates will have 0 credit card debts. Some undergraduates will have hundreds of thousands of dollars in credit card debt. So already X equals the average credit card debt carried by undergraduates. We are told that X is normally distributed with the mean. So let's see here. So X is normally distributed with the mean. So mu equals 3173 and a standard deviation of 1120. Okay. Right off the bat, we can go ahead and make the sampling distribution of sample means. So we know that the sampling distribution of sampling means is also going to be normally distributed. Why? From the central limit theorem. Because the central limit theorem says if your population is normally distributed, right, then your distribution of sample means, regardless of the sample size, is also normally distributed. So let's go ahead and we can sketch this.
It's 1645.
Thank you. So now, we label this X bar because we're now looking at sample means. So the sample means are normally distributed. And what is the mean of the sample means? It's going to be the same as the population mean, so it'll be 3173. So we can put that in. And then what about the standard deviation or the standard error? The standard error is going to be the standard deviation divided by the square root of n. Now what is n? Well, we're not sure. So let's see here. What is the probability that a randomly selected undergraduate who is a credit card holder has a credit card balance less than $2,700? Okay. So we want to know what's the probability that a randomly selected undergraduate who's a credit card holder has a credit card balance less than $2,700. What I've drawn here and what I started to draw is the distribution for the sample means, right? I don't want to know about a sample of undergraduates. I want to know about just a typical undergraduate. So I need the distribution for just a typical undergraduate, right? So what is the average, the credit card debt carried by undergraduate? Notice that this credit card debt is normally distributed, right? So the credit card debts are normally distributed. So I can draw my same old normal distribution. I know my mean is 3173. Let me actually add a page below. Okay. So let's see. So I'm drawing my distribution for the credit card debt, average credit card debt. X is normally distributed. And I know the mean is 3173. And the standard deviation is 1120. So the mean is 3173 and the standard deviation is 1120. What are my inflection points? My inflection points are, let's see, I need 3173 plus 1120. 4293. And then I need 3173 minus 1120, which is 20 53. Okay, so this is keeping track of the credit card debt of average undergraduate. So the question we're asked is, what is the probability that a randomly selected undergraduate who is a credit card holder has a credit card balance less than $2,700? So we want to know what's the probability. So we want the probability that X is less than 2,700, because X is, let me erase that average here. So X is a random variable, right? So if you ask a certain person, depending on the college student that you ask, how much credit card debt do you have, you're going to get a different answer. And we want to know what's the probability that the credit card debt is going to be less than 2,700. That means we need to shade. So I need to go over here, and I'm going to just pick somewhere in here and say this is 2,700. So the probability is going to be equal to this area. So this probability that X is less than $2,700 is equal to the area, which is going to be normal CDF. Okay, and we need to know our lower, our upper, our mean, and our standard deviation. So our lower is going to be -1E99. Our upper is going to be 2,700. Our mean is 3,173. And our standard deviation is 1120. And we are going to get normal CDF. We'll go second, bars. Number 2 is normal CDF. Lower is -1E. Remember, that's going to be second comma, 99. Our upper is 2,700. Our mean is 3,173. And our standard deviation is 1120. Paste. And what do we get? We get 0.3363952441, approximately 33.6% probability. Right? So it's kind of like saying about 1 in 3 students, undergraduate students, will have debt less than $2,700. So our answer is 0.336 is our probability. Now, you randomly select 25 undergraduates who are credit card debt holders. What is the probability that their mean credit card balance is less than $2,700? Well, now, here's the deal. Here's where we're going to use the distribution for the samples, right? So now I've got a sample. Let me copy and paste. Now I've got a sample. X is normally distributed. My population mean is 37, and my population standard deviation is 1120. But my sample mean of sample means, is going to be equal to mu, and my standard error is going to be sigma over square root of n, right? And so since n is equal to, that's going to be 1120, and since n is equal to 25, we're going to have over square root of 25. So that will be 1120 over 5. So we'll have 224. So I can draw my inflection points. 224. All right. So if I have 3173 plus 224, that'll be 3397. If I have 3173 minus 224, 2949. So these are my inflection points. Now, what's the probability that their mean credit card balance is less than 2,700? Here we go. So let's plug in our 2700. What we want is, we want the probability that X bar is less than 2700. Here's the idea. Before we stop and calculate this, you tell me, do you think that the probability is going to be less than the probability of one person having an average of less than 2700? Or do you think that our probability is going to be greater? I think the probability is going to be less. You know why? Because if we're saying that on average, students, undergrads, have 3,173, it's probably it'd be easier to find one person that has less than 2,700 than 25 people whose average is less than 2,700. Because that means you've got to find a lot of people with some low student credit card debt. So I'm guessing that our probability is actually going to be smaller than this, 33.6%. Okay? What is the syntax that we entered? This is what we want. This probability is equal to the area right here. How do we get that area? Normal CDF. What is our lower? -1 E99. What's our upper? 2,700. What's our mean? 3,173. And what is our standard deviation? 224. So we'll have normal CDF. Second bars, normal CDF. Our lower is -1 E99. Our upper is 2,700. Our mean is 3,173. And our standard deviation is 224. Enter for paste, which is equal to 0.01736. Wow. So that means you've got like a 1.7%. 1.7%. So less than 2% chance that you're going to find a sample of size 25 whose average credit card debt is less than 2,700. Wow. So that's our final answer. Okay. So we've done a lot. We have done a lot. We have interpreted, so we verified the properties of sampling distributions. Okay. We interpreted the central limit theorem. The central limit theorem tells us that if n is greater than or equal to 30, then your sample means will be normally distributed. Okay. And number two, if your population is normally distributed, I'll stop writing it because it's already written in a very lovely way earlier on in the slides. But the central limit theorem gives us two conditions under which we can be guaranteed that our sampling distribution of sample means is very close to a normal distribution, right? And then the properties of sampling distribution tells us that our mean for our sample means is going to be the same as our population mean, and our standard error is our population standard deviation divided by the square root of the size of our samples. Okay, and then lastly, we applied the central limit theorem to find probability of a sample mean. And the key thing here is that probability is equal to area under curve. So we just use our normal CDF with our sample mean of the sample means, and our standard error. All right, that's it. Thanks.